In this lesson, we will evaluate more integrals using the integration by part technique, sometimes in conjunction with substitution. First, the integration by parts formula states that the integral of u dv is equal to uv minus the integral of v du. So evaluate the integral of x squared sine 3x dx. So usually we let u equal the function who, when you repeatedly differentiate, will eventually become a constant or 0. So we're going to let u equal x squared. Du is then equal to 2x dx. dv will be equal to sine 3x. And to find v, we have to antidifferentiate this. And so that will be cosine of 3x, actually negative 1/3 cosine 3x. Cosine's derivative is negative signs, making the negatives cancel, and then you have to also accommodate for the chain rule. The derivative of 3x is 3. So the antiderivative of x squared sine 3x will be negative 1/3 x squared cosine of 3x, so that's uv, minus the integral of v du. So we're actually, minus the integral of negative 1/3 cosine 3x multiplied by 2x dx. So we can simplify that slightly. Into plus 2/3 the integral of x cosine of 3x dx. And now we can apply the technique again. This time, let u equal x, and then du will equal dx. Let dv equal cosine of 3x dx, and v will be 1/3 sine of 3x. So we have negative 1/3 x squared cosine of 3x plus 2/3 times the quantity uv. So u times v will be 1/3 x sine 3x minus the integral of v du, so minus 1/3 the integral of sine 3x dx. So that gives us negative 1/3 x squared cosine of 3x plus 2/9 by multiplying that 2/3 through x sine of 3x minus, now the antiderivative of sine of 3x is negative 1/3 cosine of 3x. So in the end we will have positive 2 over, we have this 3 multiplied by that 3 multiplied by that 3, so 2 over 27 cosine of 3x plus c. And as we discussed in the previous lesson, because this is x squared, you'll have 2 iterations of this process, of the integration by parts process. Had it been x cubed, that would have been 3 iterations and slightly evil. Now, evaluate find the antiderivative of cosine inverse of x. You know how to differentiate cosine inverse, but not necessarily antidifferentiate cosine inverse. So the only choice we have here really is to let u equal cosine inverse of x. And then du will equal negative 1 over the root 1 minus x squared dx. Now dv is equal to dx, and therefore v is equal to x. So the antiderivative of cosine x is x cosine inverse x minus the integral of negative x over root 1 minus x squared dx, or x cosine inverse of x plus the integral of x over the root of 1 minus x squared dx. Now you can use substitution to evaluate the integral of x over the root of 1 minus x squared. Let's just pick a different variable other than u because you've already used u. So let's let w equal 1 minus x squared. Then dw will be negative 2x dx, and negative 1/2 dw is equal to x dx. So that gives us x cosine inverse of x minus 1/2 times the integral of 1 over root w. So 1 over root w is w to the negative 1/2 power, and you apply the power rule, well, the reverse power rule. So we'll have x cosine inverse of x minus 1/2. The antiderivative of w to the negative 1/2 is w to the 1/2 times 2 over 1 plus c. And just reinsert what w is. So our antiderivative is x cosine inverse of x minus the square root of 1 minus x squared plus c. Now to find this antiderivative, or to evaluate this integral, we will have to use that around the world technique. Now you have a bit of a choice. You could either let u equal sine of 5x, or you could let dv equal sine of 5x. Now personally, I think letting u equals sine of 5x is a little bit simpler, because when you differentiate, you're going to have whole numbers versus anti-differentiation, we're going to have fractions. So I'm going to choose to do it that way. I will let u equal sine of 5x, and I will let dv equal e to the negative x dx. So that gives us du is 5 cosine of 5x dx, and v is equal to the antiderivative of e to the negative x is negative e to the negative x. So my original integral is equal to uv, so negative e to the negative x sine of 5x minus the integral of v du. So actually that will be plus because v is negative, so plus the integral of e to the negative x, well 5 e to the negative x cosine of 5x dx. And now we'll apply the process again. So we'll let u equal cosine of 5x, du will equal negative 5 sine 5x dx, v is equal to e to the negative x dx, and then v is equal to negative e to the negative x. So we have negative e to the negative x sine of 5x plus 5 times the quantity negative e to the negative x cosine of 5x minus the integral of v du, so we'll have minus the integral v du, multiplying those two gets rid of the negatives, and we'll have 5 e to the negative x sine 5x dx. Now distribute that 5, and we have negative e to the negative x sine of 5x minus 5 e to the negative x cosine of 5x minus 25 times the integral of e to the negative x sine of 5x dx. Now you're back to an expression that follows an integral that you started with. So you add that to this, which is what all this stuff is equal to, and you have one integral of e to the negative x sine 5x plus 25 of them will give you 26 integral e to the negative x sine 5x dx equals negative e to the negative x sine of 5x minus 5e to the negative x cosine of 5x. And now to find the antiderivative of e to the negative x sine 5x, we just divide by 26. So the integral of e to the negative x sine of 5x dx is equal to negative 1/26 e to the negative x sine of 5x minus 5/26 e to the negative x cosine of 5x plus c. To evaluate this definite integral, what I'm going to first do is find an indefinite integral just to get an antiderivative. So we're going to antidifferentiate x cosecant squared x dx. Now, probably going to want to let u equal x. So du is equal to dx. Now, if we let dv equal cosecant squared x dx, you have to remember that you actually know how to antidifferentiate cosecant squared dx. And the antiderivative of cosecant squared dx is actually negative cotangent of x. So, this will equal negative x cotangent x minus the integral of negative cotangent of x dx. So that has negative x cotangent of x plus the integral of cotangent x. Now think, cotangent is cosine x over sine x. We have cosine x over sine x dx. And now to evaluate that, we will make a u substitution, or do substitution. Let w equal sine of x. So dw is equal to cosine x dx. So we have negative x cotangent x plus the integral of 1 over w dw. So negative x cotangent x plus ln absolute value of w, which is sine of x. And then, if we're going to evaluate, find the area from pi quarters to pi halves of x cosecant squared x dx, first we'll plug pi halves into this expression. So we'll have negative pi halves cotangent of pi halves plus ln absolute value sine of pi halves minus negative pi quarters cotangent pi quarters plus ln sine pi quarters. Now cotangent of pi halves is cosine of pi halves, which is 0, divided by sine of pi halves, which is 1. So that first term we have is 0. Sine of pi halves is 1, so we have ln of 1, which is also 0, so my first term is equal to 0, minus, now cotangent of pi quarters is 1, so you have minus negative pi quarters, plus ln of sine of pi quarters, which is root 2 over 2, so ln of root 2 over 2. It isn't a very pretty answer, but the area under this curve is actually equal to that negative will distribute right here, and we'll have positive pi quarters minus ln of root 2 over 2, whatever that might be. Next, let's find the area under the curve x times 4 to the x. So once again, I'm just going to find the antiderivative of x 4 to the x dx. So if we let u equal x, du is equal to dx. If dv is 4 to the x dx, you have to remember what the antiderivative of 4 to the x is. And it is 1 over ln of 4 multiplied by 4 to the x. So we'll have 1 over ln 4 times 4 to the x multiplied by regular old x minus the integral of 1 over ln 4 times 4 to the x dx. So that's x 4 to the x over ln 4 minus 1 over ln 4 multiplied again by 1 over ln of 4 times 4 to the x. So this one came from factoring that one out, and then we antidifferentiate 4 to the x again and get another ln of 4. So now, let's evaluate this from 0 to 1. So the integral from 0 to 1 of x4 to the x dx will equal, first we plug in 1, so 4 over ln of 4 minus 4 over ln of 4, the quantity squared, minus, then plug in 0. My first term there will be 0. The second one we'll have will be minus 1 over ln of 4 squared, and 4 to the 0 is 1, so times 1. Now combining like terms, I have 4 over ln of 4 minus 3 over ln of 4 squared. In this example, we will start by making a u substitution, then we'll use integration by parts to evaluate the integral. So the u substitution we're going to make, we'll actually use w instead. So we'll let w equal theta squared. And if we do that, dw is equal to 2 theta d theta. And the thing to notice here is that you can take theta cubed and break it into theta times theta squared, and then cosine of theta squared d theta. So the 2 theta squareds become w's, and then the theta d theta will equal 1/2 dw. So we now have 1/2 the integral of w cosine of w dw. And now it's a pretty basic integration by parts problem. If we let u equal w, du is dw, and if we let dv equal cosine w dw, v is equal to sine of w. So we have 1/2 multiplied by uv, so w sine w, minus the integral of v du, so which is sine of w dw. So that's 1/2 w sine w minus the antiderivative of sine is negative cosine plus c, and let's insert what w is, and we get 1/2 theta squared sine of theta squared plus cosine of theta squared plus c. And that's a little tricky because you have to recognize how to break up that theta squared to apply these two techniques. But that's an illustration of how they can be combined to find antiderivatives. Now, given the region bounded by y equals 4 ln of x and y equals x squared ln x, find the area bounded by the regions. So here we have the graphs of these two functions. 4 ln x is blue and y equals x squared ln x is red. And first let's figure out where they intersect. Look like, well, we'll figure it out. So we'll set 4 ln x equal to x squared ln x. That gives us 0 equals x squared ln x minus 4 ln x, or 0 equals ln x multiplied by x squared minus 4. Or 0 equals ln of x multiplied by x plus 2, x minus 2. And from that we get 3 values for x. First we get x equals 1, because ln of 1 is 0, then negative 2, and then 2. Now, negative 2 is technically off the table because of the fact that you cannot log negative numbers. Negative numbers are not in the domain of the natural log, so negative 2 doesn't count. So our intersection points are 1 and 2. And the area between the curves is given by an integral from 1 to 2 of the top minus the bottom. So the upper curve is 4 ln of x minus x squared ln x dx. And let's just antidifferentiate this and then go back and plug the numbers in. So we'll have the integral Now let's factor up that ln of x. So we'll have ln of x multiplied by 4 minus x squared dx. Now, if we let u equal ln x, du is 1 over x dx. And then if we have dv equal to 4 minus x squared dx, v will equal 4x minus x cubed over 3. So an antiderivative of ln x multiplied by the quantity 4 minus x squared will be ln of x times 4x minus x cubed over 3 minus an integral of v du, so 1 over x times 4x minus x cubed over 3 dx. So that gives us ln x multiplied by 4x minus x cubed over 3 minus the integral of 4 minus x squared over 3 dx, or ln x times 4x minus x cubed over 3 minus 4x minus, this will now antidifferentiate to x cubed over 9. Now that we have an antiderivative, we can find the area under the curve by evaluating the integral from 1 to 2 of ln x 4 minus x squared dx. So first, when we enter 2, we have ln of 2 multiplied by 8 minus 8 thirds minus 8 minus 8 ninths. And then inputting 1, we'll have minus. Well, ln of 1 is 0, so we'll have 0 times 4 minus a third, and then minus 4 minus 1/9. So that's ln of 2 times, now that's 24 thirds minus 8 thirds, so 16 thirds times ln of 2, and then we have minus 8 plus 8 ninths plus 4 minus 1/9. So that will give us minus 4 plus 7 ninths, or 16 thirds ln of 2. Now that will be negative 36 over 9, so minus 27 ninths. Now in the final question, we will find the volume obtained by rotating the region about the x-axis. We are just going to set up this integral, not solve it, since so much of the important part of being able to find volumes of solids of rotation is figuring out how to set up the problem. So here is a typical slice. Now when we slice this, we are going to have circles with holes in them. So the outer radius is the distance from the axis of rotation to the upper curve, so that will be 4 ln x. And Rn is the distance from the axis of rotation to the inner curve, which is x squared ln x. And the volume is given by pi times the integral from 1 to 2, r out squared, so 4 ln x, the quantity squared, minus r in squared, so x squared ln x, quantity squared dx. Let's just simplify that slightly, but that in general is the setup. So you have pi times the integral from 1 to 2 of 16 ln x quantity squared minus x to the 4th ln x quantity squared dx. And if we can factor out an ln of x squared, we'll have 1 to 2 ln of x squared times 16 minus x to the 4th dx. And if you were to evaluate that, you would find the area, the volume of the region obtained when this region is rotated about the x-axis.